Hi, I'm Stan Farnsworth, Vice President of Marketing at NovaCentrix, and welcome to our exhibition at Printed Electronics USA 2014. Let's go take a look and see what we're doing. So at NovaCentrix, we've established in 1999. We're based on technologies for making nanomaterials that have been translated into electrically conductive inks, and also we've developed a new processing technology called photonic curing. When we look at the scope of the participation, we're involved with research and development. We also make electrically conductive inks. We have a numerical simulation called SimPulse that models the photonic curing process, and we also have production equipment. The PulseForge 1200 includes, for our R&D, includes pulse shaping. We have a scanning stage that moves up to 30 meters a minute, and I really like to emphasize the easy-to-use interface. But why look at a banner when we can look at the actual tool? Let's go see a PulseForge 1200.
All right. So, hello.
I'd like to introduce Dr. Kurt Schroeder, our Chief Technical Officer, who will tell us a little bit about the PulseForge 1200 today.
So the PulseForge 1200 is the incarnation of about 10 years of R&D and about $30 million on the part of NovaCentrix. This technology essentially is a digital oven. It allows us to do high temperature processing on low temperature materials. Now, why do we care about this? Low temperature materials are generally a whole lot cheaper, but if we want high performance out of any sort of printed electronics product, we need to have high temperature. So how can you do this? We were able to split this dichotomy by actually taking advantage of an interesting effect in which a lot of materials can actually be processed at really high temperature for a very short period of time at much, much higher temperatures than what the published maximum working temperature of a polymer is. For example, PET can normally take about 150 degrees centigrade. With our technology, we can go to about 400 degrees centigrade. Why does this matter? All thermal curing processes progress as the exponential in temperature. What this means in plain English is that you can take a 10-minute long process for processing a thin film on PET at 150 degrees centigrade and replace it with a 1 millisecond long process using our technology. When you do this, this allows you to take a large oven, such as a festooning oven that might be 50 feet high and 100 feet long, and replace it with a single tiny machine that's only 1 meter long, and use a fraction of the energy and get actually higher performance. What we have, instead of having a giant oven with rolls of material running through the system, we have a synchronized flash of light, which is basically goes at the same speed that you can actually do with the same oven. It's very tiny.
So what are we looking at here?
So what the system is this is an R&D system, and what we have here is a single flash lamp, and we have a table in which this moves underneath. It simulates a high-speed reel-to-reel system. So we place material on here, run it underneath the lamp, and it's over. And it takes just a couple seconds. So right now, for example, I'm going to bring up conditions that would be typical for processing silver. And
so this is your software?
Sure is. This is the software for the operating system that happens to be a multi-touch system, and allows us to be able to control a lot of variables. And we also have advanced simulation, which actually tells us the time temperature history of various materials when they are exposed to our beam. So for example, here I'm processing silver materials. I'm getting up to about 700 degrees centigrade, and this is done so in about 400 microseconds. So what I'm able to do is I'm able to monitor the time temperature history as a function of the depth of the material. So after we design our pulse and we decide we want to go ahead and try it, all we do is we simply hit the go button, and here we go. It's done.
Done.
I can do it again.
So what happened there?
The exciting thing about this, well, what happened here is that we actually process our material. And I'm going to process some real material for you in a second, but what's amazing is that when you have a device like this, it better be very, very safe. It's a multi-megawatt plasma discharge device. So what I can do, for example, if I can open this up, right? So if I'm processing the material, I can open it up while I'm actually processing with complete safety. So we try to make this very robust and very safe so people can have the confidence to actually use this new technology. Now, when I'm processing material, often I would like to process thin films, but sometimes I want to process thick films. And when you process something for a very short period of time, well, you can explode it because it's very, very high power on a thin film. So how do you deal with that? Well, if you go back to when you were a kid, you would end up having, maybe you would paint something like a model, and you would want to dry it really quickly with perhaps a hairdryer. Well, if you tried to dry it too quickly, what would happen is the top part of the paint would close in, and the bottom part wasn't dry, and it would generate gas and form a blister or a bubble. Well, this technology, which I'm going to show you, is actually anti-blister or anti-bubble, technology. We can take this pulse, which we have complete digital control over whatever pulse length we have, or even the height, and we can actually tune it to a substrate combination. Here we actually have the substrate, and as we change our conditions, we can actually see what the temperature our entire substrate is actually seeing as we change all the parameters. And the exciting thing about this is that we can prevent blisters from happening. And the reason we can is we can take this pulse, we can break it up into a lot of pulses. When we break it up into a lot of pulses and see the response on the screen, what we can do is we can allow for local thermal relaxation and management of gas generation in the thin film. So in between each of these pulses, we actually have a little ejection of gas to keep the film from failing. All of this allows us to be able to get much higher performance in a thick film and tune the beam to the substrate. Furthermore, we can actually take the substrate itself and we can tune these individual pulses and actually get the maximum amount of curing for a given material, actually going to the limit of the actual material. Indeed, we'll show you in detail more of this a little bit later. But what I would like to do is I would like to show you also how we go from R&D to production. So here we have perhaps 15 variables. How do you manage this? Well, one of the things we do is we have the simulation, which tells us what temperatures we're reaching. But another thing we actually do is all of this, instead of writing down in a notebook, we actually save them as files. And all of our machines have the same lamps and the same drivers. And what this allows us to do is save this as a file and email it to one of our industrial systems. So we could actually develop something on one of our R&D systems in one city and have production systems all around the world and send the new conditions to all the machines all around the world. This allows us to not do R&D on a multi-million-dollar production system. We can do it on the simple system right here. So right now what I'm going to do is I have an ink right here that is copper on top of Kapton. Now ordinarily if you're trying to process copper on any material, you cannot do this in air. And the reason is that it actually oxidizes. So what we found out about 8 years ago is that we could actually heat this up very, very rapidly and do so without having to have any special reduction oven. Normally you have to put this in a hydrogen oven. If you do it very, very quickly, you can actually sinter the materials before they have time to oxidize. And I'm going to measure the resistance of this right now. And you're going to see that it is an open circuit. It is not conductive at all. Completely non-conductive, open circuit. What we're going to do is we're going to process this, and it'll take a few milliseconds for us to process it. I'm going to load the file. And we are ready to go. Now I'm curing. let's see what happened. As you can see, the copper is a little bit lighter in color. And for this trace, we have 76 ohms. And what's nice about using copper? What's so special about copper? Well, ordinarily for printed electronics, people use silver. Silver costs 100 times more than copper. So this technology allows you to use inexpensive copper as a substitute for silver. And you cannot cure this in an ordinary oven. This technology allows you to do this at high speed. Although this machine was going very slowly, the industrial systems actually go very quickly, and all the variables here translate to the industrial system. And next we're actually going to show you some of the advanced simulation technology we use.
Sure, and on our way we're going to stop here and comment on one of the technical details of what we just saw. So what we're doing with the PulseForge tools is delivering per flash a very uniform profile of energy. And what that means is when we do the work that Kurt was doing, that we just saw on the PulseForge 1200, we're stitching together multiple exposures so that we can process a large area of material. Well, when we get this overlap, which we can engineer by setting the pulse conditions that we just saw with Kurt, then we get these small overlap areas where the sum of the energy is a little bit greater, and so we have these little bubbles. By carefully engineering the uniformity of the pulse beam and by having the ability using our digital pulse control to exactly control and set the overlap between each subsequent pulse, we can very carefully engineer the net overlap energy, and by minimizing the peak height on this overlap, we can get very uniform process energies. Our other folks that haven't spent the time or the effort or don't have the understanding of how this system works will have a beam profile that is not uniform. It's not carefully engineered. Notice that it's narrower here so they don't get as much exposure per flash. The net result of that is when we have sequential pulses, the resulting cumulative energy, the peak height is much greater. So when we're processing materials, the entire material set is either overcured or we have to undercure it they have to undercure it to keep it from burning the material. So this is a subtlety engineered into the equipment that we only realize when we're starting to do these large area materials for production. But Kurt also mentioned a handful of other parameters, and he mentioned SimPulse and how we use SimPulse as a tool for engineering pulse conditions and for engineering material selection. So let's go to our SimPulse station.
One quick note. By having engineered uniform pulse profiles allows us to be able to process a whole lot of materials people thought were not even possible with this technology. Processing the copper requires generally a very uniform beam profile. Notice when I did cure that, it was very uniform looking and very clean looking. That's the same thing with other materials such as silicon and other semiconductors, where you, in order to get really good electronic performance, you have to have very uniform processing.
So now I'm going to introduce you to Dr. Rick Zumsteg, who's going to talk with us a little bit about SimPulse, and in particular how we use SimPulse and the digital pulse shaping capability to both carefully manage the thermal profile and then also use that in designing what our substrate materials look like. So Rick.
Okay, what we have here is a way of visualizing what the thermal profile will be for a given stack of materials. So we can go here and we can create a stack of up to 7 materials, and we can change what that material is very easily just from our library here. We can also easily change the thickness of the material. And you instantly see this change of the effect of the changing variables on what the thermal profile is. So what you see here is the red line representing the temperature of the top surface, the blue line representing the temperature wherever this little arrow is, so we can change it real time and very quickly see what the temperature is throughout this material stack. And the yellow line down here is the temperature of the bottom of the substrate.
So this is a simulation.
This is a simulation.
So simulation of what would happen if you really do it.
That's exactly right. We can control the we can control the voltage, we can control the pulse length, the number of pulses we're using, as well as the material thickness. So let me go back to where I was before and take a look at this. And what you see here is something where the top surface goes a very high number, and that frequently would be objectionable, because let's say you want to really have to process at 750 degrees and leave it there for a millisecond or something, so you don't want it to overheat the material. So what we can do is we have a thing we call pulse shaping. And let me do and here, let me get this a little bit right, get this 0. And here what we've done is create a series of micropulses you see over in this part here, where we can control the length the micropulses on an interval in between the micropulse. And by doing that and doing an appropriate choice of time on and time off, we can create a thermal profile that looks like this, where the first pulse takes us part way to what we want for a process temperature, and the subsequent pulses are used to maintain it close to that temperature.
All right, so this is easy to use, it's fast, and it's for R&D.
Well, this is the nice thing about this simulator, is that we can develop something on the R&D machine, develop the processes we need for the customer will need for making his material. And then once we have all that data and all those parameters set, we can go and we have simulated how things work on other machines, and these 3200 and the 3300 are production machines, and so we can go and model what's going to happen on the production machine and control things like the number of lamps we might use in the production machine. And once we do that, we can create a data file that gets shipped off to wherever the production machine is, and they can use that and set all the parameters for the production machine without having to have people go there. And you can just simply email the file, so you can do the R&D on our R&D machines, and on one continent and on another continent have the production machine, and minimal problem getting all the data and getting the setup.
And so SimPulse is really saving a lot of processing time, because instead of having to develop a specific set of physical samples to go through and do a whole design of experiments on, in just a few minutes, a user of SimPulse such as Rick or Kurt or myself or our customers can very quickly develop the process conditions that seem to make sense, validate that on the R&D tool, and then ship it off to use in production.
So who are your customers for these kinds of products? You were mentioning people who want to make new materials?
Sure. So customers, a key customer group for us right now is in the display space. And that's both customers for our photonic curing tools, but also customers for our electrically conductive inks, photovoltaics, RFID, energy storage such as printed batteries, and then more traditional flexible circuits, albeit produced with these new manufacturing methods, are all key customer groups. So for example, on the display space, we've spent some time to develop this new electrically conductive ink. It's an inkjet ink. It's designed specifically for printing on glass coated with ITO, which is, of course, a transparent conductive oxide. We get excellent line definition, and this is a great ink for use with common inkjet printers in the space, such as Dymatics and Czar. We have a variety of other inkjet inks here that we've developed in-house based on our experience as a nanomaterials company and with the skill set of our formulations experts.
So you're at the cutting edge of printed electronics.
We're a funny company because we have expertise on the materials, we have expertise on the tools, we have expertise on the applications. So that puts us in a unique place, again, to have to be an excellent center where customers can come to us who are not experts in these areas, who are not experts in printed electronics, and we can help them with inks, we can help them with tools, we can help them with applications development. Examples of screen printings suitable for screen printing and aerosol formulation. All of our inks are formulated to be economical, to have high electrical performance, and to be suitable for different kinds of substrates and even different kinds of curing methods. So these inks can be cured, the silver inks can be cured using traditional thermal processes, but we also have developed inks which are specially formulated to be processed with the unique capabilities of our PulseForge tools. An example of that is our Metalon ICI electrically conductive ink. It's basically a copper oxide that has exactly no electrical conductivity. It's formulated with a reducing agent and formulated in water so that after the ink is printed on a substrate, this particular ink is formulated for paper. The ink and the paper are processed with one of the PulseForge tools. The water is evaporated. The copper oxide is reduced to copper and sintered, and it makes a very nice conductor. And so the key application for this product is RFID, and we'll see that here in a few minutes.
All right.
Let's go around the corner and see what else we're doing. So one of the key pieces for us is, as we start to move into production, is what is the shot quality? What are we able to do to support and sustain our customers' quality management system? So this is a true data set of over 100,000 shots taken on a PulseForge 3300 production tool, and we're looking at the energy delivered here and normalized by the average divided by the average. And what we're seeing on this is that 6 times the standard deviation is still within 4% of the total number. So this is demonstrating excellent shot control, excellent consistency, because in a production setting, every pulse needs to be consistent so that we have a uniform product quality coming out.
So you're talking a lot about pulses.
Yes.
So it's pulsing stuff on material.
Exactly. It's pulsing the flash lamps and pulsing the light onto the target material.
So the
light's the key. It's broad spectrum. It's near IR all the way down to ultraviolet. It's got a key component in the visible section. But as Kurt mentioned, it's very high intensity, and the energy that the light delivers is absorbed by the inks, which heats the inks. But because it's only in fractions of a millisecond, the substrate is not heated. We're selectively heating the inks. So on a production scale, we go from the R&D settings, we develop settings using SimPulse. So how do we put that into an integrated tool now? Well, let's take a look at this PulseForge 3200 that we've integrated in a roll-to-roll web handling system. We've got a PET substrate here. We've got a deposition system. Deposition system that we've mounted. We've got a dryer unit to help us accelerate the drying of the solvents, and then we have the photonic curing tool mounted in line. So this is an example of a production. And
so how about these guys?
We'll talk about, I'd like to introduce applications engineer Ian Rawson, who's one of the key engineers on this project.
Mm-hmm. So yeah, as Stan said, the deposition system here is the Harper QD flexograph press. So what you're looking at here is the actual flexograph roller. There's an analog and a doctor blade. What he's going to do is he's going to place ink into the gap here, which is going to meter. Okay? It's going to meter the ink so that it comes onto the flexograph plate and then prints onto the film. At that point, we're going to dry it out a little bit with the AdFOS near IR system. So you're going to see a little bit of water vapor come off, and then we're going to see a pulse of light over here, and that's actually going to cure the material. So we have a little bit of evaporation, then we have a final cure. And then we're just going to wrap it up. So
the curing means
that the particles now, they're basically, when you print the ink, there's liquids in between the particles. You need to get those out. So you get those out using a little bit of heat and then a pulse of light, and that actually centers the metals together.
And it works.
Then it works, right.
All right.
Correct. So now we're ready. Go ahead and flood it up.
Okay.
You ready?
Yep.
Starting speed 55 feet per minute, and you can see the flexograph image moving in wet, coming into the dryer, and then going through, the machine's flashing, overlapping as the material moves by. spots you want. We'll only run it for a couple more seconds.
So how many of these do you have? These machines?
Of this type, this is the only one. This is the
only one.
demonstration unit. So we're just here showing off the capabilities of what can be done using the flexograph and PulseForge. And of course the PChem ink, which is a silver ink we're loading in.
All right. So the result, what we get here is...
Yeah, can we... the result here is a piano. It's a capacitive touch keyboard, which I put into a connector over here, and then it becomes a playable piano.
So you're printing out pianos?
Yes.
All right.
Okay.
So this is a demonstration device of...
Exactly, and you'll notice that the interface is still the same. So the production tool has exactly the same interface as the R&D tool, which has exactly the same interface as the SimPulse. So it's collective, it's coherent, it's unified. That makes it translatable, and the investment that's spent on the R&D side is immediately translatable to the application side. So I mentioned earlier, RFID is an application for the copper oxide ink on a production scale. Let's go on around the corner and look at what this actually is. So one of our key partnerships is with Mühlbauer, based in Germany. They're the industry leader for RFID production equipment. We've been working with them for some time now and have a relationship where they use our PulseForge tools integrated into their RFID production equipment. We're also using our copper inks that we saw on the other side. And here's a video of actual RFID production tags that are coming off of the press. So we see our photonic curing tool. We're moving through the system. They specialize in optical inspections as well, to look at the quality of each tag before they put the chip on, to make sure that they're not putting a chip on a bad tag. But the yields are very high, and so it's a very cost-effective production tool. These tools were launched in May of 2014 this year, and are going to customers worldwide.
So this is perhaps the cheapest piece of electronic kind of technology. I mean, tags, RFID tags, there's billions and billions and billions and billions. And each of them can be very cheap.
Exactly. So the cost of these tags is actually lower than traditional technologies of etched aluminum. And the performance of these tags is as good as, or even better than, traditional tags. Now, there's some other operational benefits that make these economical. This is an additive process, so the ink is only applied where it's needed. We're not taking ink away, which would be very wasteful. This is also a water-based ink system, so we're not generating a lot of harmful volatile gases or solvent vapors that are coming up that need to be managed. So it's very ecologically oriented, it's very efficient, and the cost works out. So these are a lot of reasons why their customers are interested in these technologies, and we have a very close partnership with Mühlbauer to continue the development of and support these technologies. But there are other forms of integration as well. So let's continue going around the corner. This is a project that we're doing with Northfield Automation, which is a company based in the Minneapolis, Minnesota area. We also have collaboration with Bosch Rexroth, which is a German sensor. Rexroth, which is a German sensors and motion control company, and MSolve, which is an inkjet deposition tool company based in Cambridge. So this is a fantastic example of an international collaboration with US tools and components and European components coming together to show how these technologies integrate. So what we have here is the MSolve inkjet head, which is set up in a rastering configuration. We're printing silver ink on a coated PET. Here again we see a PulseForge 3300 lamp unit that's installed to process the inks to get an optimal conductivity, and the unit is then wound up. We also have an inspection station that does an optical check to look at the quality of each tag. This is in a different format than the Mühlbauer system we just saw. It's got different system capabilities and different production capabilities, but it's an example. We've now seen 3 examples of different types of integration, and that's really the future of printed electronics and how the space will move forward. It's companies that have a very high competency in their specific field of area, field of technology, coming together synergistically, which is getting a greater benefit from the combination. So at Printed Electronics USA in 2014, this is what we're focused on. We're focused on collaboration. We're focused on demonstrating the unique capabilities of our PulseForge R&D and production tools. We're focused on the unique capabilities of the electrically conductive inks and working together to present the capabilities to the attendees and to talk about applications.
So is printed electronics going to be everywhere in the future?
Print electronics will be everywhere. It's already moving incrementally forward. We're seeing the applications in displays. We're starting to see hints of flexible applications. OLED, more traditional display technologies are moving towards flexibility. That also has implications in lower cost components, more adaptive form factors. Automotive is a key application where we'll start to see conformal touchscreen interfaces that are molded and have complex curve structures that don't have a traditional set of fixed switches and knobs, but have a configurable display that can be adapted by designers or even third-party companies to customize the automotive driver interaction. Again, photovoltaics, stored battery, printed battery storage, and then this notion of the Internet of everything, the connectivity of devices, consumer devices, home appliances, logistical tracking, packaging. These are all applications that depend on these kinds of technologies to be implemented at very large volumes and at costs that make that feasible.
So this gives you more and more projects to work on.
Absolutely.
More and more partners. And do you have the manpower to support everybody that wants?
Right, so the space is absolutely growing. NovaCentrix is growing. We're hiring engineers, we're hiring technicians, we're hiring applications engineers to help in developing these technologies further, to help in working with our customers and incorporating them into their applications. And the entire space is definitely growing. And it's growing incrementally in small ways, and it's growing also in some large and shocking ways that will be coming out to the greater consumer here in the next year or 2 years or 5 years.